校好像有发那个，这是 Quiz 2吧的那个下来，你们可以看一下那个改的有没有问题啊？那有问题先跟助教讨论一下。那如果说有什么，再给我看，好不好 ？OK。那问一下，第一次跟第二次的 quiz 平均是多少分？
我回去上网跟你讲，我们分数有登记下来。
当然要登记
啊，对对对。
考析出来的是。OK。这样同学可不可以下课再来拿啊？下课再来拿，因为我们差不多时间要开始上课。对，反正你们的考卷不会飞走哦，不会飞走，应该不会在这边。先跟同学说声抱歉啊，上个礼拜因为我就是因为计划的关系，需要去一趟法国出差哦，去巴黎出差，就去看一些他们的运动科技，因为我参加那个计划叫做精准运动哦，就是其实有间接的帮助我们台湾的一些奥运选手。OK， 那但是听起来去巴黎很爽，对不对？对，我礼拜天过去，一直到礼拜六飞回来，礼拜六早上飞回来，中间呢这一个礼拜过得真的不晓得，早上7、8点就要出发不是起床哦，早上7、8点要出发，然后晚上给你搞到10点多才回来旅馆哦，每天行程就是参访的行程都排到满，所以讲实在话是有点累，就是那理论上我等于说欠你们，上个礼拜我们也没有课，但是上礼拜的没有课，不是因为我的关系，是因为我们的伟大的地方政府放了一个很奇怪的台风假哦。OK， 这个不是我能控制的，那我也放了台风假，我不能叫你们来上课，这个违反规定哦。那出了任何事情，辩护要负责，所以我没有办法。那上个礼拜这个当然是我出差，那我出差这件事情，我理论上还给你们，就是扣掉这个小考的半个钟头，我大概欠你们2个小时到2个半小时。OK， 就扣掉下课时间好了，就是我至少要还你2个小时的课哦。我们到时候后面再讨论一下要怎么样子处理这个，因为我觉得说这种必修课真的要补课哦，其实有点困难。你们什么时间会比较会在学校？礼拜二早上，谁礼拜二早上有课的？举一下手。哪个课这么变态，放在礼拜二早上？啊？Python。排球。OK， 这种课不去也罢嘛，对不对？开玩笑。那个要点名吗？要点名。每次都要点名。你们周末可以来吗？我周末也可以陪给你们，但是你们周末可以来吗？可能礼拜或者礼拜5下午，礼拜5下午有课的人举一下手。什么课？啊？德文哦 ，OK， 礼拜5下午上德文，我的学果然是很找不到学生这样。几点到几点？方便问吗？因为3 点到6点。那礼拜5的下午1点到3点这个时间，大家有没有补充？我不是说这个礼拜，当然可能这个礼拜，我礼拜5也有一堆的会啦，但是我会找一个礼拜的礼拜5的下午可以补课的时间再补给你们，可以吗？礼拜5下午1点到3点，我先跟大家先确认，礼拜5下午1点到3点，大家都 OK 吗 ？OK， 有人有课的什么的，赶快先讲。如果没有，我们就再举行。有人举手。
保龄球概论。
保龄球概论，也是体育课。几点到几点
？1点到3点。
1点到3点。可以翘吗？
因为每次都要去打保龄球，所以就是没有到就没有成绩。
你们的排球因为有2个人哦，保龄球概论只有你1个人哦。我如果说逼不得已，我牺牲你1个，可以吗？就是或者说到时候，因为我们都有录影哦，所以就是请你在2个演教室去看一下那个 video， 好不好 ？OK， 就这个先跟大家先确认一下，不是这个礼拜，我会在那个之前先跟大家先确认，在1、2个礼拜前先跟大家确认礼拜5的下午1点到3点。对，那虽然有1个同学有中，但是第一点他是体育课比较好像是比较少的体育课，保龄球。对啊，这个保龄球其实真的不用去上课，自己去玩就可以。对啊，还比较爽一些。好，那OK， 那我们就回到那个这堂课哦，回到这堂课。那我们上次讲到哪边呢？我已经搞到我已经头昏了。我记得我们已经讲到 determinant， 然后我们是讲到这个 recursive 定义集 ，OK， 然后再来是这个2乘2的 determinant 也有讲。I think we are at this point, right? We tried to prove this last time, but I ran out of time, right? Okay. 所以 ，OK。So this needs to be proved recursively. So according to the definition, okay, according to the definition, it's this one, right? According to the definition. So we need to prove that, okay? So we can expand this one, okay, from any row. Okay, this one we expanded by the first row, right? 我们从第一就是横的那个第一个横的这样子把它 expand 出来。那这边就是说我们可以，这边有两个，其实有两个。那其实它证明方法是类似的。Okay, the proof technique is similar. Okay, so we want to show like we can expand by using any column or any row. Okay, so since it could be any row, okay, it will be, if we can show it is the same as the second row, okay, without loss of generosity, okay. If you can show it is equivalent to the second row, then you can use exactly the same way to show equivalent to the third row, fourth row, and so on. 就是说如果你可以就是说证明说第一个 row expand 出来跟第二个 row 一样，那就是说当 expand 跟别的 row 其实是一样的哦。所以我们这边就是说，我们只要证这个东西就好。That's the only thing we need to show, okay, without loss of generosity, okay, 就是不影响就一般就是从一般系里面随便抓一个 row 来用就好 ，OK。那我们选第二个，但是我可以选别的 row， 其实是一样的道理 ，OK。Then what do we do? Okay, remember this is proved by induction, okay. On what? On the size of your matrix A. Okay, on the size of your matrix A. So matrix A is represented by n by n, right? 你的矩阵的大小是用 n 乘 n 来表示，对不对？所以就是那个 n. Okay. We will do the induction over the number n. Okay. So the base case. When n is 1, if n is 1, it doesn't matter which row you expand, right? You only have one row, right? And the result obviously will be the same, right? So this is trivial. This is trivial. Okay, 就是因为你就只有一个 element。你只有一个 element 的时候，其实你不管从哪一个 row 去展开是一样的，那你也只有这个 row 可以展开，所以它就这个东西当然是不会有问题。Check. Okay. So induction hypothesis. Okay. 我们假设n 小于 k 的时候成立。Okay. We can expand like to any other row, okay, it will be the same, okay, as long as the size of the matrix is smaller than n, okay. 那我就不用再写了，这是我们的假设。那我们的这个 induction step 就是 n equal to k。所以我们这边呢，稍微好，所以这边的话就是说，我们要秀这一条到 k 等于这一条到 k。这样子没有问题吧 ？So far so good, right? But here comes a little bit of problem, okay? 就是我们这边有个小小的 notation 的问题。你的 CE 是什么？这个 CIJ 代表什么？What is the meaning of CIJ? CIJ stands for AIG, right? I remember correct. We have AIG. But what is MIJ? The MIJ means you get rid of the ice row. J's color. Right? You get rid of the ice row, J's color. Okay? Because we are going to expand one more level. In order to show they are equivalent, we need to expand one more level. So, 我们要把它写出来了，就是说，这是我不喜欢这个证明的地方。但这个更简单的证明方法，就是说它其实是这样子。So every term, okay, involves an Nij, right? N11, N12 to N1k, and this Mij is a determinant of a matrix after you get rid of the ice row, J's column, right? 我们知道这个吗？对，这个是它那个叫 cofactor， 对不对 ？cofactor of the element Aij， 就是这个定义的方法是这样子，对，所以比较麻烦。那因为我们要再从这个地方再 expand 下去，或者说这个其实我们写的更清楚一点，这其实是这个东西。Right? 因为我们要套那个嘛，就是我们的那个 recursive 的那个 formula。那我们这边就要把它展开来，这个先用定义展开。所以当你展开的时候，你会发现你会有怎么讲？就是我把 A11那个写出来啊，就是 A11上负的1加 b 次方，这里面展开来 A11 according to the definition, okay, after you get rid of the first row, first column, the rest you start expanding on the first row. Well, there will no longer be the first row, there will be the second row, right? because the first row is gone. Okay, so but if we still allow us abuse the notation a little bit. OK， 我们假设我们把这个 notation abuse 一下，就是其实它就是这个东西呢，按照定义哦，它是什么？就是说 A 其实是 A21，A22啦，然后呢的乘上1的2加2的，这边写 n 这个就是 n 理论上是要写个 n 什么东西，但是呢这个地方呢比较讨厌，如果我们用原来的 A 来写的话，就是原来的1再把第2条跟那个就是第一个 row 剩下也是从第2个开始，这样子，然后再加上点点点。OK， 然后这每一项determine， 我只写 determine。OK， 所以呢，这里面有多少项 ？K 减1项，对不对 ？K 减1个 term， 对不对？对不对？因为我们这边现在的 size， 这个 A1原来是 K 嘛 ，A 的 size 原来是 K。Okay, this is a little bit complicated, so allow me to explain in Chinese. OK。就是这样比较复杂，所以我可能非得要用中文来解释哦。就是因为你原来的 matrix A size 是 K 乘 K， 对不对？你这边扣掉一个 row 一个 column， 对不对？所以你剩下 K 减1 K 减1，对不对？那你 K 减1 K 减1，你再按照这个 row 把它展开来，是不是有 K 减1项？这个问题没有问题吧 ？OK。然后你每一个都展开了 K 减1项，所以你这个没有 K 项，所以是 K 乘上 K 减1项，这不会有问题，对不对？对。And then, okay, remember you need to show all this mass is equivalent to this one, right? 所以你用同样的方法去展开 ，you expand the second row, okay, using exactly the same manner, and you will find one match, but it's just like a very complicated process. Trust me on that. Okay, 等于说你教错的会消掉 ，OK， 教错的会消掉。Okay, so it's a pain in the neck because there are so many terms and it doesn't look, here actually I invent this notation. I hope you don't mind, okay? But you should get my point, okay? Because 在这个下面在 expand 的时候，你是去切掉第2个 row 第2个 column， 对，然后再第2个 row 第3个 column， 第2个 row 第4个 column， and so on。OK， 然后你这样子去 match 上面那个 expand 出来的，你会有一个1对1的，因为这个跟这个可以合并，这个跟这个可以合并。OK， 那你这个跟这个就会决定你跟哪一项互相对应到，因为你把它展开2次以后，就会互相对应到。严格讲起来不是 not exactly match, but you can apply the induction hypothesis. Okay, not exact match. This part will be a perfect match. This part will be a perfect match. This part it's going to be, you can apply this induction hypothesis to find that they are equivalent, because this one, the size is smaller than n, right? Sorry, smaller than k. 这个 determinant 的 size 是比 k 小，所以我们可以用这个 induction hypothesis，OK， 去用它，然后让这个跟另外这边 expand 出来的带有 A1、A2的那一项去把它消掉。OK， 那详细的我就不去讲了，因为这个讲完可能真的要花比较多的时间，你们可以自己去把它整个完成。我给你一个例子哦，它大概是怎么样做这样子就好了。然后 Collins 类似的做法 ，Collins 是说 is you should also use induction on the column. Okay. So okay. So then, well, we have an exercise, but actually, I mean, it's not going to be exercise. We are going to talk about it in class. But, you know, so be a square matrix, okay? Then determine A equal to 0 if either A has an entire row with all 0 entries. Okay. If you have a row with all 0 entries, obviously, okay, you can just expand on that row. 你就从那个 row 把它展开来。那因为那些 row 的那个 element 都会变成那个就是每一项的会有带着那个 row 的那个 element， 所以它们都是零嘛。所以说你最后的那个就是那个 row 就是那个 determinant 就会是零。那当然 ，for a similar argument, okay, if you have a column, okay, that are all 0, then okay, the determinant of that matrix is also 0. Okay, I mean again, okay, you can just expand that matrix using that column. Okay. Another thing that will result in you know, zero determinant is that your A has 2 identical rows, okay, or 2 identical columns. How to show that? You can also do it by the induction, okay. But if you have like you know. Because, you know, we need to show 2 identical rows result in 0 determinant, okay? So, and if you want to use induction on the size of the matrix, then, okay, the base case, n has to start from 2, okay? Because if n starts from 1, you don't have you know, a case that you have 2 identical rows, right? So that's you know, obvious the case. So A1, A2, A1, A2, determinant. This one will be 0, obvious, right? you know that's going to be A1, A2 minus A1, A2. So it's going to be 0. That's for sure. Right? Another proving technique in computer science involves induction. I suppose like your discrete math teacher told you about that already. Okay. 你的离散数学老师理论上应该教过这个，就是在那个资工领域的这个证明最多的就是 induction。OK， 其次才是别的那个就是一些技巧。你们说到这，你们的离散数学老师是谁？蔡文龙老师。OK， 好，他应该肯定有讲。然后同样道理induction hypothesis。OK，n smaller than k 成立OK，but n smaller than k we have that. So when n is k, so we have two identical rows. Okay. So let's say we just name that A1, A2, AK. And another row, let's assume it's second row. It doesn't matter, but let's assume it's second row. A1, A2, AK. And all the other elements. Okay. And then, whatever you extend on the first row, it's going to give you, A1, A1. A1 times, let me just write it down, it's squared, times n1, 1, right? A2, n1, 2, right? And if you look closer to n1 to 1, n11 is a determinant, A11, right? Right? It's a determinant of A11. And what is A11? You get rid of first row, first column, first row. I think I made a mistake. I should expand on another row. It's probably better because we're going to use the induction process. Let's try to expand, like using like the third row, okay? Because they are the same anyway, right? Sorry. For the third row, it's going to be A31. Okay. The third row is going to be, power 4, and it's going to be N31, right? Plus A32. N32. Right? Right? Okay. So what is N31? N31 is determinant A31, right? Okay, so you get rid of the third row and the first column, right? you get rid of third row, first column. The rest of the matrix, you get a determinant. That's what you have here, right? 对，你拿掉第三个 row， 第一个 column， 你剩下来的你拿回去取 determinant， 对不对？这是你的那个 M3E。Okay, but remember, okay, the rest, this A31 obviously will have two identical rows, right? This A31, after getting rid of this one, this part are still there, right? This part are still there, right? So obviously you have two identical rows, right? You have two identical rows, and the size of the matrix is now what? K minus 1, right? So you have a matrix, okay, K minus 1 by K minus 1, and you have two identical rows. According to the induction hypothesis, this determinant is 0, right? 根据你的那个就是 induction 的那个假设，因为你现在的那个 size 小于 k， 然后你有两个 identical row， 所以你的这个 matrix determinant 应该是0，对不对？所以 this one is 0。Okay, for similar reason, this one is 0. Okay, So every M31, M32, M33, M34, and so on, they are all 0. So you add them up, it's going to be 0. Okay? So that concludes this induction about it. I mean, for this one, you don't need to further expand the matrix, so it's easier to describe. Okay, but the previous one, I will give you the link. Okay, for the complete proof of this one. Okay. Okay. I mean, otherwise, that proof is kind of not easy to comprehend. So I will just tell you the basic idea and give you the proof. Okay. So then, okay. If A is an n times n triangular matrix, then determine A equal to A11k times A22 times blah blah times Kn. Basically, it's the product of diagonal elements. Okay. Can you erase this? Okay. There are two types of diagonal matrix. Okay, obviously. The upper diagonal matrix, like this. This part are non-zero. This part is 0. The upper diagonal or lower diagonal. This is lower diagonal. This part is non-zero. This part is 0. So, either case, this theorem is satisfied. Okay. So, to be very honest with you, okay, we actually do not need to use any proving technique. We can just use like a direct proof. Okay. Because this one is sort of easy. Okay, so easy. So that's we can just assume we start from maybe lower diagonal. Okay, lower diagonal matrix. Okay. If we start from lower diagonal matrix, okay, the proof technique is pretty much the same as upper diagonal matrix. Anyway, okay. So determine it. So let's say this is A. Okay, assume this is our A. Determine A is going to be okay. You start expansion on the first row. On the first row, because it's the upper diagonal. Okay, so this first row, only this element is non-zero, right? Only the first element is non-zero. A11 is non-zero, right? All the other A12, A13, A14, they are all zero, right? So it's going to be A11 times what? C11. Okay. And then all the other things, these are all zero. Okay, because A12, A13, okay, all those terms, the A1I are zero as long as your I is greater than 1. Okay, and then, okay, what is C11? Well, C11 is going to be A11 times -1 squared times what? Determinant A11, right? First A11, this one is gone. Okay, this one is pretty much 1. So this determinant A11 is, well, you get rid of the first row, first column from A, but the remainder is still a lower diagonal matrix, right? The remaining matrix is still a lower diagonal matrix. Okay? Then and with like this element to be A22. Okay. Then when you want to do this, okay, it's going to be A11, keep it here. I mean when you expand this, it's going to be A22, sorry, times -1 squared times, well, you carry the first one, first row, first column. I mean, it's allow me to again abuse the notation. It's going to be determinant A11, 2, 2. You carry the first row, first column, and the second row, second column from A. Okay, and you can keep expand. This one is pretty much gone. It's just 1. So you can keep doing that. Eventually, you are going to get your A11, A22, A33, A, and then. Okay, that's pretty straightforward. Of course, you could also prove by induction. I mean, its structure allows you to do the induction, I mean, easily. Okay, so either lower triangle or upper triangle, is. I mean, of course, if you are doing like an upper triangle, I will recommend you to do the expansion by the first column. Okay, because the first column contains only one element, non-zero. Okay, non-zero, only one non-zero element. Okay， 就是如果说用这个 column 来 expand， 第一个 column 来 expand， 那就只有一个非零的那个 element， 所以那个 upper triangle 就是用 column first column， 那 lower triangle 你就用 first row。OK， 基本上。 做这个是类似。Okay, so for triangular matrix, okay, the determinant of it will be the product of its, diagonal elements. Okay, so how about this one? If A is a square matrix, we have determinant A transpose equal to determinant A. Can you prove it? Well, it's very close to the break. I will let you try it. Okay, you can try to do the induction over this property. Okay, of course, again, the induction is on the size of the matrix. Okay, and you can try to do it yourself. When we come back, we'll discuss this. Okay? So let's take a 10 minutes break.